6.5, problem number 20. This problem is about a cup of coffee which is cooling. So the problem statement is like this. So you have a cup of coffee and the coffee's temperature at time t is equal to 0, which is the current temperature, say, is 95 degrees Celsius. The initial temperature, I would say. The initial temperature of the coffee is 95 degrees Celsius, and it is given that it takes 30 minutes for the coffee to cool down to 61 degrees Celsius. Okay, and essentially the problem is we have to find out the equation for the temperature of the coffee for any time t between this time t is equal to 0 onwards, and you have to prove that Tt is equal to 20 plus 75 e to the power minus kt, where k is the constant of cooling in the Newton's law of cooling, and the Newton's law of cooling is like this. So Newton's law of cooling essentially says that the rate at which the temperature cools down, that means the derivative of the temperature with respect to time, so capital T is the temperature of the coffee, little t is the time. This is equal, it is proportional to the temperature difference of the coffee at this time and the steady state temperature. So it is the derivative of capital T with respect to t is the difference of the temperature right now, which is, I should say, dt, capital T at t, minus the steady state of the coffee. Now in this case, the steady state of the coffee would be equal to the temperature of the room, and it is also given that the room temperature, the steady state temperature, is 20 degrees Celsius. So this is the problem statement. We want to prove that this statement holds. Okay. Now how there is also so this is a proportionality, and k is a constant of proportionality. Now think about it. This is cooling, so the rate at which it cools down should slow down. So which means if the temperature is very high at this time, so the rate at which the temperature will cool down from, say, 95 to 90 degrees Celsius is much faster. So that's the way, and it has to be negative. So that's what this means. So how do you solve this thing? So dt by, so I will forget this little t here, t minus ts is equal to minus k dt. Okay, now integrate both the sides and think about this. I want to change this t to tau because I want to write down the equation at time t, and the time is going from 0 to t. Here time is going from 0 to t, so the temperature will go from T0 to capital T, T. Okay, makes sense. So take the integral, and this is 1 over x type thing. So the integral would be the natural log of t minus ts. It should be absolute value, but Ts is the least temperature, so this capital T is always going to be more than Ts, so it really doesn't matter. And the temperature is going from T0 to capital TT is equal to minus k comes out, and the integral of tau, which is a dummy variable, is just tau. So tau is going from 0 to little t. Very well. Okay, substitute. You get the natural log of t at t minus Ts. Okay, so natural log of T minus capital Ts minus, then substitute T0, natural log of T0 minus Ts. This thing is equal to minus K times T. Okay, now look at this. This thing is natural log of A minus natural log of B. We know that this is the natural log of A divided by B, the ratio of these things. So let us write down. You have natural log of Tt minus Ts divided by T0 minus Ts is equal to minus Kt. Okay, now we can say that we can exponentiate both these sides. We get e to the power natural log of Tt minus Ts divided by T0 minus Ts. This thing is equal to e to the power minus Kt. Now natural log and exponential functions, they are inverse functions of each other. Therefore you get essentially Tt minus Ts divided by T0 minus Ts is equal to e to the power minus Kt. And we know what is this thing? T0 is the temperature of the coffee initial temperature. Okay, so we know that this initial temperature was 95 degrees Celsius. Ts is the steady state temperature. Steady state, and we know that Ts is what was the steady state? 20 degrees Celsius. It is the room temperature. Okay, so we substitute these things. So 95 minus 20 is 75, and this is also Ts. So it is Tt minus 20 divided by 95 minus 20 is equal to e to the power minus Kt. Therefore Tt is equal to, okay, so this I can just replace this 95 minus 20 by 75, and I have Tt is equal to 20 plus 75 e to the power minus Kt. So this is precisely what we wanted. And it's also given that this little k here is given to be 0.02, which we will use to find the exact average temperature of the coffee. So the second part of this problem is find out the average temperature of the coffee during the first half hour. So part B of this problem is, what is the average temperature say TAVE for the first half hour, for the first half hour. And we know that the average temperature, average value of any function is equal to 1 divided by the length of the interval. Now in this case the interval is the interval of time, so it is 30 minutes, so 30 times the integral of the function, and in this case the function is the temperature of the coffee with respect to t, and t is going from 0 to 30. So this is precisely what we want to find out. So we know that this is, okay, 1 over 30 is here, integral 0 to 30 of tt we just found out to be 20 plus 75 e to the power minus kt dt. So let's integrate. So 20 is a constant which comes out. For the first integral you have 0 to 30 dt plus, then you have 75 is a constant, so 75 over 30 times e to the power times the integral of e to the power minus kt dt. Okay, So here the first integral is just t from 0 to 30. Then there is a constant 75 over 30. Now you have exponential e to the power minus kt. The integral, please check, is minus kt over minus k. Now this you can do using the integration by substitution. So you compute. So this is 20 over 30 times 30 minus 0. So this guy will be just gone. This is 20 plus 75 over 30 times minus 1 over k, and k is given to be 0.02 times e to the power minus 0.02 times t, which is 30, minus e to the power minus k times 0, which is e to the power 0. So e to the power 0 is just 1. And I got something like this. This is 20 minus 125, so the minus comes here, times e to the power minus 0.06 minus 1, and if you calculate, it comes out to be 76.39 degrees Celsius, which is warm enough coffee for you to drink.